Hi everyone, my name is Eugenia Varsev. I am a first year postgraduate student from Russia, and I would like to tell you about modeling of steel oxidation in circuits with lead coolant.
Let me start from a history of nuclear industry. More than 50 years ago, first commercial nuclear power plant was put into operation. A lot of problems have been solved since that time, such as the issue of a fuel composition selection, suitable materials problem, and construction materials corrosion. And let's look what we have today. A mature industry with advanced science, a powerful computers that allows us not only to calculate things, but visualize them as well. Let's look at the problems that we have today with advanced fast reactor with lead coolant. It is a corrosion problem again, like 50 years ago. So I want to say that we have the same fundamental problems with the new reactor systems, but much more powerful tools to solve them. The method to predict a thickness of oxide film on a steel in liquid lead has been developed. It based on a law of high temperature oxidation of steels. The set of mathematical equations you can see here. This method allows us to calculate oxide thickness. As we know, it defines a corrosion rate of construction materials in lead and other heavy liquid metals. It has a number of advantages. A dependency on the basic parameters of liquid metals, such as oxygen concentration and the temperature. This model was tested on experimental data and shows a reliable result. But this technique has disadvantages as well. And general is it shows oxidation only in one point of circuit. To overcome this, I implemented this method to CFD package OpenFOAM to make it calculate an oxidation. Here we can see the test case, an example of lead flow in T-junction, and distribution of oxygen concentration is showed in this video. The lead with zero oxygen concentration goes from the top, and flow from the left has 0.01 ppm concentration of oxygen. We can see how oxygen accumulates in the deadlock with the time. On the next picture, a distribution of oxide film throughout the T-junction surface is showed. So now I got trend of oxidation of this T-junction. From this diagram, we can see where the highest oxide thickness and the lowest one is.
And in conclusion, I want to say that this is a powerful technique that I'm working on, and I believe that it will help to solve all problems of a new reactor systems. Thank you very much for your attention, and looking forward to see you in Paris.